Okay, this is 15.6, number 3. It's another triple integral. This time we want to evaluate the triple integral of x squared dv. For the following limits, we want this function inside of a cylinder that's centered at the origin with a radius of 1, runs along the z-axis, and then we want it between two planes, z equals 0 and z equals 5. So that'll be the bottom and the top. Okay. Well, in order to set this up then, you'll notice that they just say triple integral dv. So it's really up to us to pick the right geometry. And in this case, because it's a cylinder with a bottom and a top on it, that makes the most sense. So I'm going to evaluate a couple of things here. First, the integrand. In terms of polar coordinates, this is going to be r squared cosine squared theta. So that's actually the function that will go inside of the integral. And now let's match up what all of our limits are going to be. So we're going to integrate this with respect to theta. And of course, theta will go from 0 to 2 pi, because we're going to do the full circle in order to encounter every piece of the cylinder. In terms of the r value, we're going to go from 0 to 1. So r goes from 0 to 1 because we're inside of a cylinder of radius 1. And then finally, the z value in it, of course, goes from 0 to 5. So 0 less than or equal to z less than or equal to 5. And you'll notice that all of our limits are numerical, which means we can do this integral in any order we want. So it really doesn't matter. So I'm going to evaluate this guy. I'll just do them in this order. So it's 0 to 2 pi, and then 0 to 1, and then 0 to 5. And then we write in the integrand, which is r squared cosine squared theta times r, and then the inner one was dz, the next one out is dr, and the final one is d theta. But order didn't matter on this one because they were all numerical. We can mix and match, and when we evaluate this integrand, we're going to end up with 5